Hi and welcome. Today we're going to be talking about delegation, federation, assertions, and claims. A little bit of introduction before we get started. My name is Lyle Mullican. You can find me on most social networks under the handle @Mullican. I've been working with Rails for a long time, since version 1, and I'm currently a principal engineer at paynearme.com. We are hiring, so feel free to come talk to me on the Discord chat if you're interested in exploring opportunities there. Today, I'm going to be talking about user authentication, and specifically the protocols that we use for single sign-on. Before we dive into that, I think it's worth starting with the question of why we should care about these things. As a developer, I'm probably not in the business of implementing protocol level details on a daily basis, so why should I care how they work? I think there are two answers to that. The first is that almost all of the security controls we have depend first on having a reliable authentication system in place. If there's a way to impersonate a valid user, especially a privileged user, then a lot of the other security controls that we've so carefully put in place to protect our applications become irrelevant. So I believe that security is a shared responsibility, and every developer should be as educated about it as possible. The second reason, though, is more practical. The law of leaky abstractions applies very much to the concept of user authentication. If this isn't a term that you've heard of before, it was coined almost 20 years ago by Joel Spolsky, and it states that all non-trivial abstractions, to some degree, are leaky. So what this means is that as programmers, we benefit from all kinds of abstractions that are meant to protect us from details, so that we can focus on solving the problems that we care about. But there's always some point at which those abstractions fail us, and the concerns that we're trying to avoid end up leaking through. So I think for Rails developers, one of the most obvious examples of this principle is Active Record. It's an abstraction that's meant to protect us from the database, so that we can interact with the database without having to understand how it works or to really know SQL. But I think most of us have run into cases where that abstraction fails, and either for performance reasons or some other reason, the database concerns leak through to our application, and we find that we really do need to understand things at a lower level. So the same is true of authentication systems. Even if the gems that we use or services that we rely on can abstract away a lot of the concerns around user authentication from our applications, at some point those concerns are likely to leak through, and having some knowledge of what's going on at a lower level can serve us well. So today, we're going to talk about some authentication protocols that are specifically relevant to web applications. And then we'll step back and talk about things to think about from a developer's perspective when we're integrating them, and where they can start to cause us problems. So authentication really aims to answer the question, who's sitting at the other end of a keyboard? And computers have needed to do this since they had the concept of multiple users. And this turns out to be a fundamentally hard question to answer. It really comes in two parts: how a person first establishes an identity, and then how they reprove that they are the same person when they come back later. Most of what we think of as authentication falls in that second category. And there are analogies to this in the physical world. If this were an in-person conference, then most of us would have had to board a plane to get here. I hope that we have that experience again next year. But consider what happens when I walk up to the gate to board a flight. An agent who's never seen me before, has no idea who I am, has to decide if I'm allowed to be there or not. And if you ever watch someone do this in an old movie, in the early days of air travel, it was a fairly simple process. Anyone could walk up to the gate with a ticket, pretty much, as long as they'd paid. And now we have different concerns. And airport security over time has become a lot more sophisticated. So now we have a clear separation between a secure gate area and a public area. And before I can enter the gate area, I need to provide a government-issued ID, typically something like a passport or a driver's license, in this country at least, which is a long-term credential. It's valid for years. And then at the gate, what I have to show is a boarding pass, which is a short-term credential. It's something that I can only use today for this particular flight. And that's not a perfect analogy, but most web applications are really doing something similar. Every request that my browser makes to reach a protected resource has to include some kind of token that the software answering that connection is able to trust. So traditionally, we would do this with a long-term credential in the form of a username and password. It's kind of like that government ID in that it doesn't change that often, but I can provide it once and get back a session cookie, which acts as a short-term credential. It represents then my identity from that point forward for all of the other requests that I make in that session for whatever the definition of a session is to that application. So there's a separation then between the validation of a long-term credential and a short-term credential that I exchange it for. And often that just means different pieces of the same application doing different jobs. But the fact that there is such a separation means that other authentication models are possible too. So if I were to just create a new Rails app, I might do something like this. This is called local authentication, because my application has direct knowledge of the user's long-term credentials. Now, the passwords are stored as hashes, I hope, but this application is taking user input and computing that hash to store it and to verify it. So it has access to the user's credentials. And this kind of authentication has a very long history. We've been doing this since the early days of Unix, at least. And it has a lot of advantages. It's simple. It's reliable, it's easy to test, easy to reason about, easy to understand. But just like the threat model for air travel has changed since the 1960s, the threat model for software has too. In the modern world, storing a local database of password hashes really means that we need a lot of other supporting infrastructure, things like this, and probably a few more things that I didn't think about. It's really a lot to take on. And maybe not every app wants to deal with all of those things. But it's also not just the threat model. Software architecture has evolved too. So there are a lot of cases where local authentication really starts to become a problem for the way that we build software. Use cases can include having multiple applications that have a common user base. If you have several different applications because you want to build things in self-contained components, but you need to seamlessly transfer people between them, then local authentication can become somewhat challenging. If you have client-side code, JavaScript running in the browser, or a native application that needs to fetch private data from multiple sources, local authentication becomes a problem. Or my favorite use case is the one where you have a hosted software as a service kind of product and you just landed a huge enterprise client who loves it, and they're going to bring you 30,000 users, but they don't want those users to create accounts. They just want to click a link on their intranet and have their internal identity, which they manage themselves, magically transfer over to your product. So if we already validate those long-term and short-term credentials in different ways, it's not hard to see that those actions could be handled by completely separate applications rather than just different parts of the same application. Now that identity validation could be handled by some centralized system that you own and control, or by a third party that you've outsourced the job to. But there are a couple of related terms that you'll hear in these conversations, which I think are helpful to define up front. So federation means that within some defined environment, there's a central source of information about users, and other systems are able to rely on that single source of information. Single sign-on then means that as a result of federation, that from the user's perspective, because that single source of information exists, they can take one set of credentials and use them to access many different applications. So let's take a look now at how that's actually done and what implications these protocols have for the way that we build software. So the first one that we're going to look at is SAML. This stands for Security Assertion Markup Language. It's been around for almost 20 years, so whether you've had to work with it directly or not, you've probably heard of it or been exposed to it in some way. This is a standard that's maintained by an organization called OASIS, the Organization for the Advancement of Structured Information Standards. Sorry. And this was probably the protocol that they are best known for. It was the first single sign-on protocol for web applications that really got very wide adoption. So by the mid-2000s, a lot of big organizations like Google and Oracle were using SAML in their products, and they were advocating for other people to adopt it as well. Now, like all new standards, the early versions had some issues, so there were a couple of revisions to it, and 2.0 is really what everybody means today for the most part when they talk about SAML. Now, I think the name of the protocol is a little bit misleading because SAML is much more than a markup language. The specification covers both the format of messages and the way that they're communicated between systems, so it is truly a protocol. And there are a few other terms that are more specific to SAML that I think are helpful to define as well. So an identity provider is the system that holds the user information and checks passwords typically, and a service provider is the thing that the user is trying to access. An assertion then is a statement that the identity provider makes to the service provider about the user. And an assertion could be positive, saying, I recognize this person and here are all the things that I know about them. Or it could be a negative assertion, which says, this user's login failed. I have no idea who this is, and therefore you should not trust them. So this is what an assertion looks like. And this is actually about the simplest possible version of one. So as you can see, they're XML documents and they're pretty big in general, which can sometimes be a problem, and we'll talk about the ways in which that causes problems a little bit later on. But one important aspect of SAML is the fact that authentication can be started at either end. So as a user, I can start with the identity provider and say, authenticate me to this service that I want to access. Or I can start with the service, and I can say, ask this identity provider to authenticate me, and either one of those are valid workflows. There are a few different ways that the messages are actually exchanged between the systems. Those are called, in SAML terminology, bindings. So SAML is really designed for web applications, so everything happens over HTTP, but that can be a GET request, a POST request, or a slightly more involved process called artifact resolution, which we'll see in detail here in a minute. So this is a lot of terminology, so let's try another illustration to make it a little bit more practical. Let's imagine that we have a library of rare books, and a patron named Alice who wants to see one of them. So the book is a protected resource. So Alice goes up to the fiction desk and she asks to see their first edition of The Hobbit. So Bob, the friendly librarian, tells her he's actually not the one who's allowed to check library cards. So Bob redirects her over to Carol. Carol is the person that the library trusts to validate library cards. So that is her job. So Alice goes over to see Carol, and Carol asks her for a library card. Alice provides it, and now Carol can look up Alice's record and make sure that she's a registered patron in good standing. She doesn't have too many fines. She hasn't left fingerprints on any other rare books. And she's satisfied that Alice is a good patron of the library. So here's where it gets interesting. Carol has a special fountain pen that she keeps locked up in her desk. So she writes out a letter to Bob, informing him that she has reviewed Alice's library card and record and determined that it's all valid. So she signs the letter with her special pen. She hands the letter then to Alice and tells her she can carry it back with her up to the fiction desk. So Alice does that. She delivers the letter. Bob recognizes Carol's signature because no one else has a special fountain pen like she does, and then he's able to give the book to Alice. Now this is more or less how a service provider initiated SAML login happens, with either the HTTP redirect or post bindings. So the way this becomes single sign-on is that the identity provider is typically maintaining its own session state for the user. So now if Alice goes to the nonfiction desk and she asks for a different book, she can talk to Dan. He's going to redirect her right back to Carol again. But this time, when she talks to Carol, Carol says, "Oh, you were just here. I recognize you. I don't need to see your library card again. I'll just write out a new letter for you right away, and you can take that back up to the desk. So this is a fairly seamless handoff then. Alice is able to exchange that letter with Dan for the book. So that was essentially what the service provider initiated process looks like. For the identity provider initiated process, we would just have Alice go to Carol's desk at the library as soon as she walks in. So she would immediately take her library card to Carol. She would tell Carol what desk she wanted to access, and then Carol would still give her the signed letter just as she did before. She would take it to the desk and she would get her book. But this time, critically, the first time Bob saw her, she already had that letter in hand, so he didn't have to do anything except check it. Now, in both of these cases, even though the letter was really a communication from Carol to Bob, you notice that it was Alice who carried it and delivered it. This is actually pretty common in single sign-on implementations. The user's web browser is used as a vehicle to transfer information between the two parties. Now that's really convenient, but you can imagine that there's some risk associated with the fact that Alice has control over a document that Bob is going to rely on to prove her identity. And we'll talk a little bit later about how that can play out in some interesting ways. But for SAML, there is also another way of transferring the assertion, which I mentioned earlier, called artifact resolution. In this case, what happens is that after Carol writes out her letter, she tucks it away in her desk, files it under a number so that she can find it later. She writes down that number. She does really have lovely handwriting. And that's the only information that she gives to Alice. So Alice gives that number to Bob, and when she does that, Bob is able to go over to Carol's desk himself, ask her to retrieve the letter that belongs to that number, then he can read what it says without Alice ever having seen it or touched it. Now this setup is slightly more complex, of course, because the identity provider has to store assertions. It requires direct communication from the service provider to the identity provider, and that's not possible in all situations. But it does eliminate some categories of risk. So, speaking of risk, in a system like this, the fundamental question is, what makes that assertion trustworthy? Especially in those scenarios where the user was in control of the message. So a service provider gets a statement about a user, and unlike a password, this doesn't require some kind of pre-shared exchange of secret knowledge between the two of them. So the service provider needs to be sure that the assertion wasn't forged. That if I could just create valid assertions on my own, I could pop one into my web browser and impersonate any user I like. The service provider also needs to be sure that I can't capture an assertion today, then use it again tomorrow if my access was revoked. That I can't capture an otherwise valid assertion and change any part of it before sending it on, like changing the user ID, changing a failure status into a success status, changing an expiration time, changing the audience. If I could get a valid assertion for one provider and then take it over to another provider, it shouldn't be accepted. So it turns out there are a lot of different attributes that are really important for an assertion to contain, and all of those need to be trustworthy in order for the system to work. Now, SAML supports both encryption and signing of assertions. So you might be tempted to think that one or the other is enough, but most of the time encryption doesn't help too much with this problem. Unless you're using an authenticated encryption mode, which can be done, but it isn't really all that common in SAML implementations, an encrypted assertion only guarantees confidentiality. It does not guarantee necessarily that an assertion hasn't been manipulated. So for that, what we have to rely on are digital signatures. Now, the technology for digital signatures is well established. The math behind them works. So that's not generally the problem. But unfortunately, there are a lot of ways to still get the implementation of digital signatures wrong. And in the case of XML in particular, there's a lot of complexity around it. So XML, if you think about it, doesn't care about spaces, tabs, line breaks. All of those are pretty irrelevant to an XML document. But in a signed document, every byte is significant. That's the whole point of a digital signature, that if one byte in the message is changed, the signature becomes invalid. So to sign an XML document, in order to make sure that all systems handling it can process it exactly the same way, you first have to canonicalize it, which means transforming it in a very specified way before signing it. And you can also choose to sign all or only part of a document. So both of those make XML signatures fairly complicated. And this is one of the things that can make SAML hard to work with. Both creating and verifying signatures is fairly complicated, and in the worst cases, that complexity has led to vulnerabilities that completely undermine the whole system. So I'll have a link to a research paper at the end of the presentation that shows some practical examples of how that's happened. But remember also that assertions are usually pretty big documents to begin with. Adding signatures only makes them bigger. They're base64 encoded, that adds about 20% to the length. And parsing XML is a moderately expensive process to begin with for most systems anyway. So at scale, processing SAML assertions can really become a performance problem. Partly for that reason, SAML just doesn't work well for applications that have a lot of JavaScript running in the browser and making queries, authenticating itself to APIs that are providing data. But for the IDP-initiated workflow, it may be your only option, because a lot of other protocols don't handle that use case very well. So for that enterprise client scenario, SAML is often what you're stuck with. But what are some other options? Not too long after SAML 2.0 was published, another identity-related protocol called OAuth came along. Now, OAuth had its roots with Twitter, but it ended up becoming an IETF standard. So it's important to note, though, that in this case, the auth in OAuth really stands for authorization rather than authentication. It's an important distinction, but an unfortunate overlap of prefixes in English. So the idea with OAuth is that you want to delegate your identity on one site to another site. So, for example, if I had a WordPress blog and I wanted it to tweet for me every time I publish a new article, OAuth gives me a great way to do that. I can sign into Twitter with my username and password. I can get back a token that represents my identity, probably with a limited set of permissions associated with it, and the WordPress server, or whatever it is, can use that token then to interact with Twitter's API as me. I'm essentially authorizing WordPress to represent itself to Twitter as me. I'm delegating my identity. But since the process of delegating my identity required me to log in and prove my identity first, it was tempting sometimes to see OAuth as a way to do single sign-on or delegated identity management. And on the surface, it does look pretty similar to what we saw happening with those SAML workflows. I have a service provider that can redirect me to another platform where I authenticate myself, and after logging in, coming back with a token, and the original service provider didn't have to know anything about my credentials. If that token is valid, if it works for accessing the other system, then it must mean that I proved my identity over there. But in practice, that turns out to not always be a true assumption. And I'll also have a link to some research at the end of the presentation that illustrates the cases where that's not true. But beyond that, it's a little bit like in that library analogy, if Alice, to prove her identity to Bob, gave him a key to her apartment as a way of doing that. Now, he could certainly go to her apartment and unlock it and look around, find some personal information, and he could probably conclude that her possession of the key meant that she was who she claimed to be. Most of the time, that conclusion would probably be correct. But it's not really what the key is meant for. And she really shouldn't have to give Bob access to another system just to prove her identity. So OAuth is not really a great fit for a situation where we really just care about identity verification. But OAuth as a protocol does have some really nice advantages over a protocol like SAML. For one thing, it has much smaller and JSON formatted messages, which are much easier to parse and pass around, and it has workflows that are specifically designed for mobile and browser-based scenarios that SAML doesn't address very well. So the smart people who make standards decided to make another protocol that was layered on to OAuth called OpenID Connect. And it uses many of those features of OAuth that are so nice, but it adds some additional ones to more specifically and formally address the needs of an authentication workflow instead of an identity delegation workflow. Now this is different than an earlier standard that was just called OpenID, so there is some shared history and relationship between the two, but OpenID Connect is much more recent and in a lot of ways has replaced OpenID, so that's the one that I'm going to talk about today. And there are also a lot of shared concepts with SAML. So many of those single sign-on redirects that we looked at before are similar enough that we don't need to go through them all again, but we will highlight what a few differences are. And there's some slight differences in terminology as well. So we have still an identity provider, but most of the time the system that we're trying to access is now called a relying party. You will also hear the term service provider, but the idea here is that the service I'm trying to reach can rely on statements that the identity provider makes about me. And there are a few different kinds of tokens associated with OpenID Connect. So we have an access token, and that is part of the OAuth specification. So that would be the thing that WordPress could use to access Twitter's API. What OpenID Connect introduces is a new token called an identity token, or ID token, and this ends up being somewhat like a SAML assertion, in that it contains information about the user. That's the thing that the relying party is going to rely on. So attributes of the user here are called claims. SAML would typically have called them attributes within an assertion. And as I said, messages are generally formatted as JSON, which is more compact and a lot faster and easier to parse than XML. For an identity token in particular, we have a very specific JSON structure associated with it called a JSON Web Token, or JWT, which you've probably heard of or worked with before. Now, one other really nice feature of the OpenID Connect specification is its discovery protocol. So this allows an identity provider to publish a lot of its configuration information under a well-known URL path, which is the same for all providers, and it reduces the amount of upfront setup then that's required to do an integration. So SAML had the concept of metadata files, which kind of did the same thing, provided a lot of the information you would need about an identity provider to configure it, but they still generally took some manual effort to work with. OpenID Connect's discovery is a lot more standardized and lightweight. So here we have Google's OpenID Connect metadata, which gives you pretty much everything that you would need to use Google as an identity provider. So the main advantages of OpenID Connect over SAML are that it has smaller messages, that they're faster to parse and process, that it's usually easier to get an integration set up, and it's built on a protocol that anticipates the more modern use cases that we have for JavaScript-heavy applications and native mobile applications. But just like with SAML, there are several different ways of using OpenID Connect in practice, and they do have different security implications, so let's take a look at those. The first is the authorization code flow, and this exists in the standard OAuth 2 workflow as well. It's a lot like the SAML artifact resolution protocol, actually. So what happens here is that after a user authenticates to the identity provider, and they're redirected back to the relying party, what they have in that redirect is an authorization code. So this is just an opaque token that doesn't really mean anything. The relying party uses that authorization code together with a secret that it has to make a call back to the identity provider and obtain both an access token and the ID token from the identity provider. So again, it's the addition of that ID token that's unique to OpenID Connect. The rest of this is part of the OAuth 2 workflow. So this flow is going to work, though, for a more traditional server-to-server kind of interaction, because you notice that call to the token endpoint required a client secret. And JavaScript running in the browser, or even code running on a native mobile platform, cannot keep secrets from the user. But if you're dealing with a server that can, then this works pretty well. And sometimes the access token is still needed. It still has uses in OpenID Connect, even if there's otherwise not an API that you're trying to access. Most identity providers provide what's called a user info endpoint, where the relying party might use that access token to query the user info endpoint and get more attributes back about the user who's logged in than were contained in the ID token. So ID tokens typically need to be fairly small for a couple of different reasons, one of which being the way that they're passed around. So a lot of times the ID token contains only the minimal amount of information about a user, and you might still want to call this user info endpoint to get additional attributes. But for those cases where the code that needs to know something about the user can't keep a secret, JavaScript, for example, we have different flows. And for a long time, the one that was used most was the implicit flow. Now, this is today largely considered deprecated, but not everybody supports the newer standards, and so this is still in use in a lot of ways. So what happens here is that instead of providing a secret in a separate call, once the user has authenticated with the identity provider, when they're redirected back to where they came from, they get the ID token included in that redirect, and can also have an access token as well, but the ID token is the one that's most relevant here. So this process is not necessarily broken or insecure, but it does make some security trade-offs, and those weaknesses can end up creating major problems if they're not implemented exactly right. And so generally you don't want to use this flow if you can avoid it. Since the client can't really prove its identity to the identity provider by nature, the identity provider can only have a pre-configured list of redirect URLs that it is willing to send users back to. So you have to have those pre-registered in advance, and they have to be validated in order for the system to work at all. And the tokens themselves can be passed in a couple of different ways. They can be passed on the query string, or they can be passed as a URI fragment. But if they are passed on the query string, then they're more subject to being leaked. And anything passing in the front channel, again, is under the user's control. So there are a lot of ways that these tokens could end up escaping. So JWTs also support different signature algorithms, and not all of those will work in this configuration either. So, for example, an HMAC-based signature algorithm requires a pre-shared secret that's known to both parties, and so you have to rely only on public key signatures, which are stronger anyway, so that's not probably too much of a drawback in this situation, but they do generally mean longer signatures, and so that's a consideration as well. And so there are just a lot of reasons why the implicit flow can be problematic. The more modern way to handle that use case is with an additional step called Proof Key for Code Exchange, or PKCE. And what this does essentially is to allow the public client to derive a temporary single-use secret for each authentication, and then it can use that for making token requests through the authorization code flow that the server would have used. So this is definitely safer and more robust than the implicit flow if your environment supports it. There is also a hybrid flow, which has some features of both the implicit and authorization code flows, but the use cases for this one are pretty narrow. It's mainly useful for an app that wants to identify the user early on in the process and do some kind of handling of that data, but then still needs an access token to make other calls. So it's not one that's widely used. So this is generally what happens in OpenID Connect. Most single sign-on processes that you encounter today in production are probably going to be using either this protocol or SAML. So now it's time to step back and talk a little bit about what all this means to me as a Rails developer. Back to the first question I asked, which is, why do I need to care how any of this works? It's a lot of protocol detail. But as we said at the beginning, authentication, although it's a hard problem, is one that the vast majority of web applications have to deal with in some way, and it underpins a lot of our other security controls. As you saw from the history of these protocols, pretty quickly after there was a version 1.0, there was a version 1.1 and a version 2.0, and that's because as these things were adopted, researchers started looking at them and seeing them in use and finding problems with them, even after very smart, capable people had developed the specifications in the first place. And now that the protocols themselves have been through that and matured, people still find problems, but they tend to be at the level of implementation, and that's where it starts to matter to us as developers. So vulnerabilities are often subtle, and they're usually in implementation. And I think that should tell us a couple of things. First is that most of us probably don't want or need to implement these protocols at a low level directly. It's better to rely on code that's been tested and looked at by a lot of people. That doesn't mean we don't need to understand it, though. I'll show you a quick example related to JavaScript web tokens, or JSON web tokens. So this is what a simple JWT looks like. It has 3 parts. They're separated by dots. The first 2 are just base64 encoded JSON strings. There's a header and there's a payload. And then the third part is the signature of those first 2. So if I wanted to write some code to parse and validate JWTs on my own, I might do something like this. Split the token into those 3 parts, decode the header and the payload, figure out who it was that issued this token, and go look up their signing key because maybe I support multiple issuers. And they publish, since this is an RSA public and private key pair that they publish their public key with their discovery info, and that's all that I need. But I do need to know the specific algorithm that they used for signing, because there are different versions even within public key algorithms, so they could have been using RS-256 or RS-512. But now that I have that information, I can validate the signature. But this is a problem, because what I just did was I trusted the algorithm that was declared in the token's header. And JWT supports many different algorithms, including symmetric algorithms, where you have the same key used for both signing and verification. So if you think about this, if I am checking this signature with an asymmetric public key, which I retrieved from the discovery information, and someone then feeds me a token that claims to have been signed with a symmetric algorithm, if I accept that and I process the signature as if it were signed with a symmetric algorithm, then anyone could give me a forged token that I will consider valid because the public key was available to everyone. Now this may seem like an obvious mistake, but a few years ago a researcher found a number of widely deployed JWT libraries doing exactly this. They were vulnerable in this way. There's also, it's worth noting, an algorithm of none, which is defined in the spec. And that's valid. In fact, it's required to be supported by implementers of JWTs, but it is intended only for very specific use cases. So what happens if someone just makes an unsigned token and feeds it into my app with the none algorithm specified. People have made mistakes with that too. So these kinds of issues are not unique to OpenID Connect and JWTs. There have been similar implementation mistakes made in SAML as well. And none of that means that we should avoid using gems, other people's code, to do this kind of thing, but rather the opposite to me, because I don't want to repeat the mistakes that other people have already made and fixed. But it does mean that as implementers, we have a responsibility to make sure that the gems we're using are maintained and patched and responding quickly when security reports like this are made. Now, when it comes to anything related to identity or authentication, especially once we outsource that authentication to some external system or code base, is really important to constantly ask ourselves, what assumptions am I making about the data that I'm receiving? So even if we're incorporating code from a really well-tested and well-trusted gem, or we're using a third-party platform to do all the heavy lifting for us, there's going to be some integration point with our app. And that's where we need to look carefully at what assumptions we're making and ask ourselves how our trust is anchored in any piece of data. So here's another really simple example. Let's say that my application doesn't implement OpenID Connect directly. I use something to do that for me, but I do let people sign into my application with one of several different providers. Now, not all of these use OpenID Connect, but some of them do. Now, the email claim is one that's pretty standard. Everybody's going to give that to me. So with local authentication, it's pretty common to treat the email address as a unique identifier for users. And as long as my code is validating that to be the case, I can safely make that assumption. But now, if I have several different services available that are passing that information to me, they may all handle email addresses very differently. Maybe one of them lets an email address belong to multiple accounts. Maybe one of them doesn't do a verification loop, so anybody can add any email address to their own account. OpenID Connect gave me a way to trust that the claims came from the provider I thought they did. But that's really as far as the trust goes in terms of the protocol. So now if my assumptions about the meaning of any of the information I receive don't line up with the identity provider's assumptions, I could easily do dangerous things with that information. And this, again, is a pretty basic example, but sometimes assumptions can be subtle and hard to uncover. So to kind of wrap up here, I think it's important to note that we can trust the protocols and the cryptographic algorithms that are behind all of this. These are amazing tools that give us a lot of flexibility in the way that we can design authentication systems and perform authentication for modern web applications. You can trust the math behind these protocols, but at the same time, they are sharp knives, just like Rails itself. So we have to use them carefully. Always remember that an identity token is, at least in most cases, just another form of user-controlled input that you can only trust in very specific ways. So the signature guarantees the integrity of the message, but we still have to be careful with the content of the message. And we can think about what can go wrong and plan ahead for failure cases. So it's not that hard to write tests for our application that cover many of these important validation scenarios. So what happens if we receive a token that contains itself malicious content of some type? What happens if I inject a token into my application that it didn't ask for, wasn't expecting? What happens if I strip off the signature from an otherwise valid token or play around with the algorithms? What happens if I give my application a token that was issued to a different application? Or what happens if I replay an expired token? And as I said, if we're trusting gems to do this kind of thing for us, it's very critical to keep them patched. But it's also not just the technology that can fail. At a more systematic level, if you're planning any kind of single sign-on implementation or delegated identity management situation, there are several other things that you probably want to consider before making the decision to delegate this most critical function of your application to a third party. What happens if they experience a breach, or if they're down, or if they get acquired by another company, or just change their privacy policy in ways that you didn't expect? It's important to realize that single sign-on also creates a single point of failure, so you want to plan ahead for what those failure cases might look like. If you want to learn more about how these protocols work in practice, especially in the context of a Rails app, I think it's useful to stand up your own local copy of both an identity provider and a service provider and see how the messages are exchanged and play with that from both ends. It's a little bit easier to do that for OpenID Connect than it is for SAML, so I recommend trying it that way. You can use the Doorkeeper OpenID Connect gem to stand up an identity provider pretty quickly. There are a couple of web-based tools that you can use for understanding different parts of the process. So jwt.io is a live debugger that you can use for inspecting JWTs, see how they're put together, how signature construction and validation works. And oidcdebugger.com is kind of an OpenID Connect playground where you can step through all of the different flows associated with OpenID Connect and see what's happening along the way and kind of decode each interaction, and it makes it pretty easy to do that. And as I promised, a few links to interesting related documents for further reading. You can read the specifications themselves. They're actually very readable, I think, and helpful for understanding how these protocols work. There's an article here from OAuth.net about why specifically OAuth does not work as an authentication protocol. The original article on the law of leaky abstractions is definitely worth a read. And then a couple of research papers here about some of the implementation problems that have been found around JWT and SAML libraries. And I will mention again that Pay Near Me is hiring, so please come talk to me if you're looking for a new opportunity. And thank you very much.